Hey everybody, this is Larry. This is me making an attempt to do a problem that I haven't done before. Have I done my steps today? I'm just trying to find the difficulty level. Okay, I did my step this hour, or my standing up this hour. So let's do a hard one, because I want to have time for it. That's why I'm like looking at my watch. Okay, so let's do a random hard one, and let's do it together. Let's do one that isn't an SQL problem. Okay, cool. And today's bonus question for me is, again, not a premium question. I never get these non-premium questions when I didn't have premium, but I don't know if this RNG is biased or something. I don't know. Anyway, today's problem is 1157, online majority element in subarray. So design a data structure that efficiently finds the majority element in a given subarray. The majority element in a subarray is an element that occurs threshold times or more in the element or subarray. Okay, so you have an array, and then you query the left, right, and then okay. That's interesting. Maybe. What would be okay? I mean, I'm thinking about a few things. One is that the first thing I was thinking about is what is his name's algorithm? The one that just checks majority, but it's not even necessary. It's not even necessary that, I mean, they call it a majority, but it's a little bit awkward because there's a threshold as well. So yeah, so 0 to 3, 3, 2, 3, 2, okay. So it's a little bit awkward. There are a couple of ways you can think about doing this, and that's what I'm kind of thinking about in my head. I don't know that they're right or not, but they're at most 10,000 queries. The length is 20,000. So we may think about different ways of processing it, right? And the first thing that I'm thinking about is just kind of this prefix sum type thing of okay, let's say we have a collection on each element, and then you kind of do a difference of those things to kind of get the so that you can answer the query, and then just check for something with is in check if something is in the threshold or something like that. But that's potentially n square space if every number is different, for example. So I don't know that I can do that for 20,000, right? Because that's like 800 million, something like that. I can't do math. 400 million, whatever. So something like big enough, right? Uh, yeah. So I can't do it that way. The second way that I'm thinking of is maybe something similar, but either with one of the two things. One is the sparse table, a log n table, and then the other is square root decomposition. Both of those things are kind of really high powered, so I'm just trying to think whether there's a more biased thing about it. But if you wanted to kind of read up about it, the sparse table and square root. Well, I guess I could type out square root decomposition. I think we can probably use yeah, I mean, I think definitely this. I don't know if it's true, so don't hold me to it. But the square root decomposition should be good. But I have to try to think about. I'm just trying to think about whether there's like a more first principle type thing, because these are kind of heavy machinery, to be honest. And can I do something about the threshold? Because you can't really do like the naive way, which is just to loop for each query. But of course, this will probably be too long. But if you do square root of n and then 22 square root of 20,000 is what? Like 140 or something, right? I don't know. 141 maybe. Yeah, close to it. I know that one from like 1.41 is you go to square root of 2 or something, give or take. Obviously, I'm not one of those people who memorize these things, but it's just when you have done enough math problems, maybe it comes up. But anyway, so that should be okay with square root decomposition. Okay, let's do it with square root decomposition. I think I still want to say that maybe there's a more easy way, to be honest. But I don't even know. Can I do it that way? Well, what I wanted to say was that if that's the case, then we could play around with learning something new. At least for me, because I haven't done square root decomposition in a while, but I think I could prove it from first principles on that. But let's say that we are able to do it. Is there a way to, or like, how would we compose the answer for each square root component so that we can be reusable, right? So that part is still actually not clear. I think I skipped ahead a little bit, thinking that it might be, but I mean, I guess we can do the prefix something and then just kind of accumulate. If we have square root elements, so what was it? So I said there's 141, so what's 20,000 times 141 is 2.8 million, which honestly should be good enough. But Leetcode is kind of silly with constraints, so I'm not confident about Leetcode being able to do this per se. Am I missing a really obvious answer? I mean, it has to be at least majority. I don't know that I know this one, to be honest. Oh, I mean, I can do it the other way and maybe just using a different language. 3 million is feels like it would be fast enough, to be honest. But, you know, like I have to change language, but is it Freud's majority algorithm? So I feel like it's someone famous, but I always forget the name. It doesn't really come up that much. But I don't even know how I can get it to apply here. Well, I guess in the case where there is like ridiculous amount of things, well, then each query will still be 20,000, right? If you do a prefix sum on 20,000 different things, so maybe that doesn't quite work. Even if the 2.8 million is a little bit fast enough. Huh? Is there any like? That shows. Okay, so it has to be at least half. Is there any principles that we can think about? Like I'm just trying to think through like whether maybe there's a pigeonhole principle or something like that that I can think about figuring out. And this isn't even one of those problems where you know the query ahead of time, so then you can kind of pre-process the way specific to these queries. Because then you have to pre-process everything in a regular way or already. I don't know. What's n over log n again in this case? Log n is going to be... No, the square root of n is going to be better a bit. There's just so many distinct elements. And you don't really want to add... I mean, I guess there's the other way of just... There's going to be square root of n elements in each of these, and then square root of n of all those. So then that's... I mean, that's over 20,000, but then that just becomes linear in the worst case. So then I don't know that that would be good enough to do, to accumulate in the regular way. I'm kind of stuck on these high power things. I'm going to erase them so I could maybe think about another for it. I don't know. I don't know that I know this one, to be honest, but there's also like maybe a segment tree, but I feel like that's also kind of... Yeah, I don't know if segment tree is kind of the way to do it, but... Is there a way we can... trying to think whether there's any way I can like binary search or something like this, but there is a fun randomized algorithm, I think, but I don't know that that's kind of... I haven't done randomized algorithm in a while. Can that be right? I mean, what are the odds we have to say, right? Well, if a majority exists, then if a majority exists, then in so if a majority exists, then you get the right number 0.5% of the time, right? And so that means that, you know, if you want to do it 10 times, is that true? I mean, yeah, so you could pick like 10 random numbers from the interval or something like that, but then I don't know that they're random because that means that if there's only one, that mean okay. So let's say you have a range of 20,000. If you pick 10 random numbers from the array and there's a majority, then you will pick the majority element. What if there's a majority element, you will pick it 1 in 1,000 times, right? 2 to the 10, 1 over 10,000, or 1 minus that, 1 over 1,000. So you have a 99.9%. And you can even pick like 20 numbers. Okay. And then 20 numbers will be 1 in a million anyway. Okay. So let's say we have a number. How do we check? Well, one way that we can do is prefix sum or something like that as we set for each number, but that's kind of, the other way that we can do it is with index. You can do binary search on the beginning and then on the thing to count, and I guess that's maybe okay. Let me play around with that. Okay, so something like no, is equal to okay, and then now for index x in enumerate or self dot indices of x dot x, right? And then now we can maybe do something like count self left right x, right? And then now we do bisect left on left. Is that the, I think actually that's not the syntax though. Maybe something like this. Right, and that would basically be the numbers that are smaller than it, and then bisect left of bisect right. So we want the next number, so all the other numbers will be smaller than that, right? So let's go to this. I think this is right. Maybe it's mine off by 1 because I'm always really bad about it. Yeah, okay, maybe. And then now here, let's just say R is equal to okay, so if right minus left is greater than 20, say, let's just call it some random number, it doesn't really matter. I mean, it gives us, every extra one gives us half of it, but okay, yeah. Is there a, I feel like there's a Python thing that just gives you 20 elements, but okay. So if it's less than 20, then we just do a for loop, right? C as you go to collections.counter. We might not even need to do it that way, actually. Yeah, maybe I could just do something like this. But you may get the same index, so I think that's a little bit awkward, but maybe that's fine. X is equal to right minus left. I have to think about how to randomize this in a correct way, because sometimes it's very easy to do on off by 1. All right, let me look up the ran.ren thing as well first. In Python, I always forget how to do it. Doesn't really come up that much. Random.ren range. Okay, that's actually pretty helpful. then I don't have to do fancy math. So left, right, is it inclusive? Matches of range, so it's not inclusive. So it should be this +1. Okay. I'm just testing it real quick, making sure that okay. I mean, it gives me random numbers. That's fine. I don't know. Looks random enough. Okay. So then now, okay. So now, oops. Given that, if this all fails, then we return -1. Otherwise, we count the number of occurrence here. If count of if self.count left, right, I think I did it with inclusive, x is greater than or equal to threshold, then we return x. The code is actually pretty simple. Whether it is right or not is a different story. Will it be right if I, what do I return? The element, right? Yeah, okay. So I got 0, but I get 0 to 3 wrong. Oh no, it's expecting 1. Did I do it wrong? I mean, like, this may be off by 1, that's why. Oops. Left, right, or left, minus that +1. I mean, it should be off by 1 because otherwise, you know, it shouldn't be expected -1 and 2. What? That doesn't even. Okay, let's see, fella. 0, 3. We should do the x. And it's giving me a different answer every time, but okay. 0, 3, 2. So 0, 3, 2. We counted 3, which is definitely not right. 0, 1, 2, 3. So this is the third index, and then bicep left of 0 is 0. So this actually returns 4, but that 4 isn't right. Wait, is this it? Maybe I'm confusing things a little bit, but I think the idea is right. Well, it's probabilistic, but you know, I am curious what the intended solution is, but so I don't know that I know this one. Okay, so then it tries 2, 0, and then R is, oh, I have to return the index, not the thing. So no, this should be right. It finds 2, right? So okay, so maybe I just don't need the +1. I'm mixing different things in my head. Okay, well, I mean, this is kind of randomized, so not quite sure that this works, but let's give it a submit. Oh, in terms of like there may be an off by 1 or something like this. And yeah, let's see whether I'm just unlucky. Like if I ran it again, would it still be wrong? Okay. This is just really bad. I mean, this gets a random range, but what I need is a number from that random range. That's why this is wrong. Okay, that is just a silly mistake. I can't even get this point right. This is silly. Okay, fine. I'm actually surprised that passed like 12 test cases or something, right? Out of like 25 or whatever it was. Does it tell you again? No, it doesn't tell you anymore. But it popped up very briefly. But yeah, what is the running time? Like, oh, actually, it's still pretty fast. This is a very hard problem, I think. I don't know what the intended solution is. But this is actually pretty cool. It's randomized algorithm. The idea behind randomized is, you know, this you have to figure out the randomized space that it is in, and it actually has a different type of complexity analysis, which I don't want to get into it too deeply because, frankly, I don't know it anymore, or like it doesn't come up enough for me to remember it. But there are basically stuff that, and I'm just like doing a little bit hand wavy. Definitely look into it if you're really interested. But the idea is that there's this concept in randomized algorithm called with high probability. Even though that sounds like even though this sounds like an English thing, like something that you say in English, it actually has a specific mathematical definition, which means that it basically has some like O of, not O of, I forget the exact notation, but basically you have like the probability for not n, maybe n is not the quite, I don't remember the right terminology anymore. It's really random that it comes up. I am ready, whatever. But basically, it's an algorithm that you can reduce the quote unquote error in terms of this basically 1/2 to the x for some x that we can choose, right? So basically, you can say that yeah, and this is actually things that kind of comes up in stuff like proof algorithm or zero knowledge proofs and stuff like that. But I'm not going to get into that much as well. But basically, the idea is that we can choose it for some x, and that x depends on how comfortable you are. And here we can kind of work toward proving this, right? So there are two things. One is time complexity, and the other is kind of the randomized proof. And like I said, I'm really excuse me, I'm really out of shape on this one, so definitely please well, one, correct me in the comments if I say something wrong, but also two, if it's a little bit hand wavy, that's my fault. But you know, hopefully at the very least it's sparks interest for you to kind of just, you know, do something or like do more research into it, because Larry is old and don't remember everything, and it's not like I'm a professor or something. So yeah, but basically the proof, right, is that okay, let's say this is a random number in the range, right? So there are two cases, right? So let's say a majority exists, right? If a majority exists, then what happens? Then here, this will pick the majority 1/2 time, right? 1/2 of the time we will pick a majority, because that's the definition of majority, right? Like it's more than half the element, or half or equal, or half or more of the element, or someone, I don't know how they define exactly with the off by one, but you say close to half, right? So if we run this 20 times, we have 1/20, 2 to the 20, or you know, 1 in a million chance of picking the wrong element, right? Every time, or 20 times, right? Does that kind of make sense? Basically, you know, this is because you only need, if we run it 20 times, you only need this to be correct once to be correct. So therefore, if we run it 20 times and we choose a random number, then the only times that if we're really unlucky and we run it 20 times, right? And we get it wrong 20 times. Okay. So then if majority not exists, then 0% of the time we will pick a majority, right? And this is correct 100% of the time if majority does not exist. So that's basically the idea. And combine these two, you could think about it in a different way, but yeah, but that's basically the idea. And of course, this is going to take O of m times, O of m iteration, because it's not O of m time. And each of these do a count, and this count, of course, is just going to be log n, right? So it's going to be O of m log n time, and O of n space, just, you know, making this index, right? The one for each element, so it's O of n space. That's all I have for this one in terms of my explanation. That's actually, I am actually curious because I don't know how to do this one really. Randomized algorithm is something that I took a long time to pull out the bag, because it's not something that I kind of think about that much, to be frank. So so let's see. Discussion majority. What is this? Is this 4 different solutions or what? So yeah, I'm just reading it together with y'all, so definitely check that out. If majority is order dependent, if the majority is okay, wait, what? Oh, okay. I am curious about this because that's the way that I was thinking about with square root decomposition a little bit, but I wasn't able to prove it in my head. But I guess they didn't really they didn't prove it either. They just kind of stated it. So okay, Baltimore. That's the name that I was thinking of. I thought it was just I don't know for some reason I thought it was Freud. So yeah. And then you could merge the things. And then build an interval tree. I'm not a sig tree. That's a ridiculous solution. I mean, it's not that it's ridiculous. It probably is right, but it's just a really hard problem to kind of think about, right? Okay, so basically this is the same idea, but instead of randomized, it's seg tree. And apparently there's a paper that this is a ridiculous problem, but apparently you can also read a Chinese paper to do it O of n. Is it OMQ? That's what I was going to guess. How would you think about OMQ in this way? And that's actually I said sparse table, but I didn't really, and you know, sparse table is you can use the sparse table to do the OMQ as well. But I didn't. I didn't know how to make that extension, but apparently it exists. So I wasn't that far off. But yeah. Huh. Well, I don't know. That's not even a solution, but okay. I mean, I think we were kind of close, but I don't know. You want to say that, but segment tree buckets, but they didn't do. They didn't talk about the OMQ solution or the square root. Is this a square root decomposition? I don't know. I don't know. I think that's all I have for today, though. Seems like there are a couple of segment trees, which I'm not going to get into. This is a ridiculous problem for an interview. I like my solution. Let me know what you think. Maybe I'm going to make it slightly smaller. Huh, it was a little bit bigger than I expected. So you can kind of see all the code kind of thing. Okay, but yeah, that's all I have for this one. Let me know what you think. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.